10, 9, 8, 7, 6,
Oh, this
5,
is cool, actually.
4, 3, 2, 1. Ignition. And liftoff. Liftoff.
Hello, I'm Brian Cox, and I have the tremendous privilege today to be joined by Project Staff Scientist Sam Howell, who is a staff scientist on the Europa Clipper mission, and we are going to watch the launch from Banana Creek live. Sam, it's great to see you again. Last time we spoke, actually, last time we met was in Alaska. We were filming for my new series, Solar System, and in there we discussed in some detail what we might find at Europa. But that was a long time ago, it feels now, but here it is on the launch pad.
Thanks for joining us here at Banana Creek. I've been now working on the Europa Clipper mission for about 8 years. When I started, it was a paper study, and I've been here through our formulation and building out the spacecraft, assembly testing and launch operations. And it's pretty surreal to see it sitting across us here on the pad waiting to go.
It's about, what is it, about an hour before launch?
Yeah, we're just about an hour and 4 minutes until liftoff, if all goes according to plan, and have a great view right about here of our rocket sitting across the water on the launch pad.
So the launch window to get to Jupiter, perhaps you can comment on how difficult that is. Isn't it about a minute or something like that?
We have what we call an instantaneous launch window. So that is, we have about a 1 second wide window for launch. And you can imagine, we're not going straight to Jupiter. We have to go and fly by Mars first in February and grab a little momentum. And then in December of 26, we'll fly by Earth and grab a little momentum. And it won't be until the spring of 2030 that we actually get there. So all of those little errors add up. And you really want to make sure that Jupiter is there when you arrive a little under 6 years from now.
Yeah, so it's a 1 second launch.
It's a 1 second launch window. Though we have that 1 second opportunity every day for about the next month.
It gives you a sense, doesn't it, of the precision of these orbits. As you said, it's 1 second and then arrives in 2030.
Yeah, it's truly amazing, especially given that, there's sort of 3 rocket systems here. You have the first stage booster on the Falcon Heavy. It's 2 boosters attached to it, the second stage, and then our 24 rocket motors on the Europa Clipper spacecraft, all just to get to Jupiter. And yeah, it really gives you some perspective on just how difficult it is to hit that moving target from 5.5 years out.
Isn't this the largest spacecraft or the most massive spacecraft that's been sent to Jupiter?
Exactly. It's not even the largest and most massive spacecraft we've sent to Jupiter. It's the largest and most massive spacecraft that we've ever sent into interplanetary space in general. So we're a little over 16,000 pounds heavy with fuel. And when stretched out, the wings of our spacecraft go just over one hoop of a basketball court to just over the other. This is truly a massive spacecraft, fully deployed. The solar panels are more than 30 meters across. And it's going to take a lot of fuel on a very big and primed rocket to get us there.
And could you give us some background as to why we are interested in Europa?
The Europa Clipper mission is really the 4th mission in a series of outer solar system flagships that NASA has undertaken. The first beginning in the 60s with the twin Voyager spacecraft that visited each planet, and the second, Galileo, to Jupiter, and then finally ending in 2017, the Cassini mission to Saturn. As we've been marching out towards the solar system and have plans to go to Uranus eventually next, we're stopping and returning to go back to Europa. This will be the first NASA flagship mission ever to target a single satellite, because we believe Europa has potentially the best chance in our solar system of creating habitable environments that could allow the emergence and persistence of extant life, perhaps even today.
Can you give us a sense of this world? Because it's about moon. It's a planetary-sized object orbiting around Jupiter, isn't it?
Yeah, and world is really the right word. This moon of Jupiter, it's one of the 4 largest, we call the Galilean satellites. It's right about the size of Earth's own moon, but if you look at the river behind me that feeds into the ocean, if you've ever stood at the shore, you can imagine what it feels like to look out and think of all of the water on Earth, the deepest extent of all of these oceans covering our globe, even though it's only the size of our moon, Europa has twice as much liquid water as all of the Earth. But it's not accessible on the surface. So if I pull up my not to scale Europa here, we see that there's a lot of different surface features showing up. A lot of these long lines that are as big as the world is. And these are actually huge cracks opening in an outer icy shell that covers the ocean from space. So it's a very geologically active world. And in this shell, perhaps 15 or 40 kilometers thick, there's lots of ongoing geology similar to our own plate tectonics, and underneath a saltwater ocean perhaps 100 kilometers deep covering the entire globe.
So what are the things that we need to know? You've given this outline. So we know there's an ocean. We know there's geology there. What are the big questions, particularly in the context of searching for life?
Right. So the goal of the Europa Clipper mission is not to directly search for life, but to understand whether or not Europa is a world that could be habitable, whether life could have emerged there and persist today. And so it's actually a bit of a complex question. It doesn't look like you might imagine the search for life. It's not a question of, lightning in a bottle with some tar and bugs crawl out. It's really geology and geochemistry and observations of the ice shell in the ocean. In a very simple way, we think that Europa's ocean is on the order of 3.5 or more billion years old, about as old as our own oceans. And where that water is interacting with Europa's seafloor, you get half the chemistry that you need for life. You get the production of something called reductants that have an electron they want to give away. All life that we know of relies on the transfer of an electron from a reductant to an oxidant in order to fuel its metabolism, cell mitosis. And so in a world like Europa, you have the production of these reductants at the seafloor, but you're still missing. It sounds like we're about to start fueling and things are still looking on track. The other half of the chemistry you need for life is somewhere for those electrons to go. And the surface of Europa, that red striped surface, is irradiated by the Jupiter environment, creating oxidants. And the geology there can bring half of the chemistry of the life on the surface down into the ocean and potentially sustain a habitable environment. So it's this really complex story, but the goal of the Europa mission, our Clipper mission, is to test all of these intricate parts that come together to create a potentially habitable world.
And then could you describe what's going to happen? So we're going to see the launch. This Falcon Heavy is going to take off into the Florida sky. What happens then?
The first hour is really going to be our transfer to orbit and lining the spacecraft up, giving it the velocity it needs to go to Mars and then eventually Earth and then eventually arrive at Jupiter. So during that first hour, we'll see the rocket lift off. We'll see it break into its second stage. About an hour after liftoff, the second stage will release the spacecraft. We'll be under spacecraft power. A few hours later, we'll deploy our solar panels and experience our first moment with the sun going power positive, which is, a real nail biter. And then over the next month or so, we'll end up deploying all the instruments. We have deployable radar and magnetometers. We'll check out the instruments and make sure that they're all performing like we expected, and be ready for a flyby of Mars in February. So today we're going to see the rocket lift off, separation, and then release of the spacecraft about an hour after lift.
And how long initially do you expect the spacecraft to make observations of Europa once it's in position?
Our current plan is for 49 science flybys of Europa, 53 in total for this trajectory. And that's going to take a little under 4.5 years.
So it's worth emphasizing, isn't it, that this is a once in a career mission. These don't come along very often, these missions of this scale.
This is sort of a once across multiple careers mission. There are people who have been working on this concept in the science team is champions for more than 2 decades now that will be on the mission for 2 more. That
I mean, when we first met, we were in Alaska about a year ago, weren't we? And we were talking then about these questions, the very basic questions. Like we see geology on the surface, which seems too energetic. We don't really know how it can be that the ice fractures in this way. As you said, maybe it's thinner than we expected. So very basic questions, really, about this world. But what we do know is that there's an ocean below the surface. We're pretty sure, very sure about that.
I was actually going to show some of the tectonics, but being a very lively crowd out here today for the launch, I think that beach ball has now disappeared.
Is it gone?
The thing that really drew me to Europa originally is looking at its surface and even thinking about those massive tides we talked about. There just doesn't seem to be enough energy to produce the modern day activity we see. But one of the reasons we believe that Europa is capable of bringing this radiation produced chemistry on the surface, half of the food you need for life, down into the ocean where the other half we think is waiting, is that when you look at the surface of Europa, it doesn't look like the surface of our moon. It's not heavily cratered. When we look at Earth, it's not heavily cratered, even though it's larger than the moon and there are more impacts. It's because plate tectonics and erosion slowly erase that surface and they erase the record. When we look at the surface of Europa, we find almost no craters at all. In fact, it seems like the entire surface of Europa has been replaced since about the time the dinosaurs died on Earth. All I have to say, we don't even have a great understanding of how thick the ice shell is. I published a paper recently saying maybe around 27 kilometers, but as much as 100 and as little as 10. We really don't know. I think the amount of immediate science we're going to start being able to do in 2031 is really going to be transformative about how we think about not only esoteric problems like Europa and its energy balance, but our own place in the universe, the importance of water and of geologic change and how these can come together to support worlds, like our own.
I'm just watching the footage as well. I've got more information than you have probably there, but I saw that the second stage is now fueling.
You probably won't be able to see much, but just across the water here, I have a pretty good view of the tower. And feeling, you can see I can see a plume of white smoke coming off as that densified liquid oxygen is added to the spacecraft.
Yeah, I can see it on this screen here. This is
an important moment. This means things are going very well right now because it's hard to unfuel a rocket.
Yeah, well, the count's still going down. The thing that surprises me actually, or interests me about this launch, usually, I think we're used to seeing holds in rocket launches, aren't we? Quite often. I've watched a lot of rocket launches as you have, because it doesn't really matter so much when you launch it. But it is fascinating for me. I don't know if you know, but I'm trying to remember a rocket launch that I last saw that had to go to the second or not, or it doesn't go. That level of accuracy, that's quite unusual, isn't it?
It is. Orbital dynamics are complicated, but we've also been assured by our partners at SpaceX, who are providing our Falcon Heavy for launch today, that they're pretty good at what they do. And,
Yeah, I remember seeing John Young, the astronaut, though, once. He's one of my heroes, that flew the first shuttle, of course, say that smile when he said, yeah, it's, maybe it's almost routine. And then he smiled. Space flight is never routine, is it, I suppose?
No, it continues to be the case that space is very hard. We've had, even just this last summer, no shortage of what the team affectionately calls curveballs, either to catch or to bat away, being thrown at us constantly from our spacecraft and for launch. And really, you carry a lot of accumulated heartbreak and anxiety with you to a launch pad, and it's really fantastic. So to have it all distilled down, 8 years of my own life and decades more for others, and across a 300-person science team and the thousands that contribute to the mission, just all distilled right now into the fairing of that rocket.
Well, well, you made it, and I just wanted to, before I leave that engineer, and I just wanted to say that as I said, I saw it, and it's a big thing. It's a big spacecraft, and it surprised me how big it is. But the level, obviously, it's intricate, it's complicated. It's a very, very, very complicated and beautiful machine. So I just wanted to pay tribute again, having seen this thing, to you and the engineers and everybody who's worked on this for decades, because it's an astonishing piece of equipment.
People see it for the first time. You know, they think, okay, it's kind of a body with some solar panels slapped on. That's what we do all the time. And what they don't see is how incredibly complex it is to take this 10-instrument flagship habitability surveyor and stuff it all inside of that central module with its 2 big solar panels.
We're talking about a piece of electronics here that's got to work for 2 decades or so, right? Or a long time, well over a decade, in a hostile environment. And it's got to be launched on that beautiful rocket behind you. It's not a usual piece of hardware.
It's difficult to communicate just how unusual it is. When NASA takes the flagship up, it's not as though, you start by going to the previous mission, picking the parts you like, and upgrading the ones you don't. Each one of these is really a bespoke and unique piece of robotic hardware, purpose designed to be the best scientist it can for its mission objective. And so for us, this is not any off-the-shelf spacecraft. It is the best spacecraft you can possibly build to understand the habitability of Europa as we understand it today. And I agree. When you think about the beginning, back in pre-phase A, and even the people that came before me, how you start with this idea of Europa's habitability and you distill it down into this now built machine being fueled on a launch pad is pretty incredible.
Because by the way, I should say 15 minutes to launch and the clock is still ticking down. So it's...
I felt the nerves a little. We were talking about the entire accumulated experience of my professional career sitting on top of that rocket right now, as I see the little puffs of cryogenically cooled water vapor drifting off. But about 60 seconds before the launch or so, a minute or so, I'm going to go and watch the show.
Yeah. So the work is ongoing, of course, in this. I mean, again, when we met, you were testing a drone, sort of an underwater drone in similar habitat, not similar habitats, but in Alaska that was in the case. So subsurface, subglacial lakes. So that research is always ongoing, and these obviously the engineering challenges are always being discussed.
Yeah, absolutely. And in fact, next summer I'm leading a team to go to the Juneau ice field in Alaska, where we will use a melt probe, we call it a cryobot, to descend through 1,000 feet of ice while sampling its environment. And rather than putting light detection instruments on board, as one might imagine for a future mission to Europa, we're actually going to have a thin sample tube back through the entire power tether of the system into a clean room we're creating inside a tent, where glacial microbiologists and astrobiologists will be there replicating a light detection payload for a planetary body. And our hope next summer is to conduct this analog mission where we descend through 1,000 feet of ice into a subglacial lake while using a science team remotely to give us feedback and drive that process as though they were a team on Earth exploring Europa.
The thing that many people will be interested in are the cameras, because it's worth reflecting that we have these beautiful images of Europa from Galileo, now Juno as well, but they're from a long way away. So, and I know that we met, I should say, we were filming for a series, and so we have imagination. I used our imagination. What would it look like? What would the surface of Europa look like? And I think you helped us with those graphics. So we almost have a record of what you think a close-up shot of Europa's surface will look like. But could you give us some sense of the detail that we expect, the resolution on those cameras? You said a few kilometers, 20 kilometers away from the surface, 25 kilometer flybys. We're going to get detailed. We're going to see a surface we've never seen before.
It's going to look, Europa already looks like a new world, unlike any other surface we've ever seen. The most detailed images we have, and I encourage you to go look up the most detailed image of Europa's surface. It's on the order of 5 to 10 meters per pixel. So if you think about that, you know, you might have trouble resolving a small building as smaller than a pixel. For hype's coming up. For the Europa Clipper mission, flying 25 kilometers off the surface, our high resolution cameras are probably going to give us sub-meter per pixel resolution for much of the surface. So we're talking about truly being able to resolve, you know, rock and boulder scale features on this alien icy terrain. It's going to look unlike, I think, any image we've ever seen from elsewhere in the solar system.
And there are cliffs. It's a jagged. So it looks smooth in the distant images. Right? It looks like this smooth, icy surface, but there are cliffs and canyons. It's quite rugged, isn't it? We think.
Yeah, well, it's jagged. It looks very jagged, and it's made by tectonics similar to those that build the mountains and the oceans on Earth. But the actual height of the topography is pretty limited. The highest point on Europa might only be a couple hundred meters above the lowest point.
Really?
And so it does look very jagged and intense, but countdown news. It looks very jagged and intense, but ultimately the topography is not very high, and so while these cliffs are rugged, they're potentially very short.
Yeah. But you mentioned then, because we've got a few minutes left, the potential future missions. I remember talking to you a while ago now, and you'd said, you know, you'd hoped perhaps your career would then be designing a submarine, a lander to go down. So if everything stacks up, as you said, this story, it really looks like this is a habitat. It's a potentially habitable world. Then where are we going next? Where does the design begin to shift? What's the next flagship mission to Europa?
Yeah, you know, you will find no shortage of competing ideas on what should come next for Europa. And of course, NASA hasn't selected any mission beyond Clipper to go there. But one real difference I think we have in the exploration of Europa compared to something more familiar like Mars is that Mars, we had this philosophy where we did our flybys and then we orbited and then we landed and then we started moving across the surface. On Europa, well, there's certainly a distribution of geology and interesting things to see. The question of life is really answered by going down. And my career hope is that we get there, find that this is an active world and not only habitable, but potentially inhabited. And then to answer that question by returning, and a concept I and many others work on is a potential future mission is thinking about how you might land and then melt through that ice shell to actually see inside the ocean and directly detect what's there. But in the meantime, we have every single instrument we would need to understand if that habitat might be there about to launch from the pad.
I'm going to let you go in a minute because I think, you know, after decades of work, you should have time to meditate a little bit.
Yep. So it sounds like we're preparing for the launch itself now. Oh, go ahead. Honestly, I am thrilled to be a part of this team. I'm very grateful to have gotten to spend these 8 years with brilliant scientists and engineers contributing one small part of this fantastic and complex mission that really is going to revolutionize how we think about things as fundamental as water. I think one of the great moments in this process has been the U.S. Poet Laureate, Ada Limon, wrote a poem that is now engraved on our spacecraft heading to Europa. And a line in that poem is, "Oh, second moon, we too are made of water." It brings up these themes of what does that mean to us and what does it mean if it's elsewhere? And I'm looking forward to finding out. I really appreciate the chat, Brian. It's great to see you again. I could use a little bit of that Alaskan weather as I bake out here in the Florida sun, but I'm very excited to see this rocket finally go.
Thank you, Sam. I really appreciate you giving us this time. I'm going to say What's the traditional thing to say? Godspeed, isn't it? Godspeed, Europa Clipper.
Thanks much, Brian. And I'll see you on the other side.
Ready for launch. And Europa Clipper getting ready to lift off.
And there's a great update as now it vents out the locks inside the line of the transporter erector. We are inside of 30 seconds.
30 seconds and counting.
I probably should be speaking or commentating now, but I can't speak, so I understand very well why Sam wanted to go away with a few minutes to go, because even I can't speak.
Minutes, 15 seconds and counting.
And here we go. 10,
10,
9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff.
Well, it's
Liftoff
going.
for Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Engine chamber pressures are nominal.
See that the chamber pressures are nominal as we hear all 27.
Oh, this is cool, actually.
Great.
Rocket beginning to roll, putting down 5.1 million pounds of thrust.